And yep, the floor is now yours.
Thank you very much. Good afternoon. First, I would like to thank the organizers of the FISO Telecon, especially Dan Lester, for inviting me to present here on the next generation space transportation that may be able to play a key role in opening the multiplanetary civilization. The drawing in the first slide shows a Starship Enterprise working on a small asteroid using phaser near a large asteroid or a small planet, which is drawn by Samuel Royal. It looks like some of the asteroids contain a large amount of gold. I believe a similar space endeavor is one of the key human space activities in the multiplanetary civilization in probably 50 years. And here I present on how to get there with Photonic Laser Thruster. I have given a FISO presentation on Photonic Laser Thruster in 2016, and since then, the technology and the space industry have made an impressive stride and become much more promising in opening space-based civilization, thanks to the rapid progress of the conventional rockets by SpaceX, NASA, and other space tech companies. Because of these developments, I am confident now that we, the human species, are on the verge of transforming from the Earth-bound species to the multiplanetary species. Specifically, NASA and ESA are planning to demonstrate ISRU and the space mining on the Moon in several years. In addition, NASA and the JAXA have been working on characterizing and landing on asteroids. In several years, it seems that SpaceX will send humans to Mars for aiming at building small habitats that may be self-sufficient. If successful, this will be truly a momentous event in human history. Beyond becoming the multiplanetary species, now we can envision to build the multiplanetary civilization that involves planets, moons, and asteroids for permanent habitation, mining, farming, and transporting precious local commodities such as gold and other metals and other components, transportation of humans and animals, energy transportation, communication, and infrastructure development in the solar system. In doing so, the whole solar system can be a habitat for humans. Where are the promising precious commodities and resources in space? I believe they are mostly in the asteroid belts. In fact, many of them are ready to be harvested or mined. Recent development on asteroid mining shows that there are enormous numbers of asteroids rich in precious commodities and even water in the asteroid belt between Mars and Jupiter, as can be seen in the left diagram. The number of dots are probably underrepresented and enormous, and many of them are small enough maybe we can just carry around by rockets. I am confident that Mars can be potentially the gateway to asteroid mining to access these history-changing resources. This is because of Mars's proximity to the asteroid belt, low escape delta V, thin atmosphere, and abundant local resources, and many other favorable factors. This also potentially makes Mars an ideal manufacturing or refining hub. And of course, the Mars has some sunlight so that one can build solar power as well, along with some other power technologies. The first group of asteroids, Hungarians, are about 0.5 astronomical unit away, which is about 75 million kilometers away from Mars. The main groups of asteroids spread between 1 to 2 astronomical units away from Mars. The natural resources that can be mined in the asteroid belt is astronomical, literally, and I predict that these will empower the multiplanetary civilization. Here, the natural resources mined from asteroids can be transformed into products that can be used on Earth and Moon and in space. Truly, the economic possibilities are enormous, and these activities further protect our precious Earth from over-harvesting or over-mining that are happening right now and about harming the Earth environment. To enable human activities for the multiplanetary civilization, especially asteroid mining, we will need a new rocket engine beyond the conventional rocket engines or thrusters. In his recent talk on making life multiplanetary, Elon Musk of SpaceX summarizes such a need here. Quote, why are you using combustion in rockets and you have electric cars? Well, there is no way to make an electric rocket. I wish there was. End of the quote. This statement emphatically crystallizes the need of a propellant-free propulsion for opening the next level of human space activities to establish the multiplanetary civilization. I am here to present that the answer to this wish may be closer than what we think and believe. Based on our extensive research results, we project that opening the multiplanetary civilization will require a new propulsion system with a delta V greater than 100 km per second. That is about 10 times of what delta V achieved with conventional thrusters, and electric thrusters without using propellant, high ISP, high energy to thrust conversion efficiency, high reusability, and many others. We are confident now that the solution is the photonic thruster or laser thruster, that is the electric thruster with the photons as propellant. In parallel to the rapidly evolving space technologies, photonic technologies, especially high-power laser technologies, have exponentially grown recently. Such growth can be seen in laser machining, fiber optics, laser power beaming. In particular, on the lower right corner, the directed energy applications have established the technological foundation for photonic laser thruster. In fact, out of the public domain, a lot of technologies dramatically evolved. Therefore, we project that infusion of photonics into space technologies is critical in opening the multiplanetary civilization. Especially, space-based high-power lasers are proposed to be crucial here. This picture shows what happens when a 30 kilowatts laser beam is directed on a car hood. It clearly burns through the hood with a flame in short time. In fact, the industries and the militaries are developing high-power lasers with the powers approaching 1 megawatts currently. And in addition, the tracking of unfriendly moving targets is rapidly developing, which are what we need for photonic laser thruster development. An interesting question is, what would happen when a 450 kilowatts laser beam, which has 15 times more laser power than the one in the previous slide, is directed on an object? Next slide shows the results. Like in this picture, a 450 kilowatt laser beam was directly on a 1U cubesat, which was demonstrated under the auspice of a NIAC program over NASA. Yes, the video shows the acceleration and deceleration of the cubesat with the laser beam. Two strange phenomena are indicated by the demonstration. First, the cubesat is accelerated without being burned here. Second, the smallness of the laser beam diameter and the size of the laser system. A typical 450 kilowatt laser system currently would have the size of a small building, but the laser system shown here has a small size of a small refrigerator. So, what is happening here? The picture shows the anatomy of the demonstration, which explains why. First, the satellite is equipped with a high reflectance mirror with a reflectance greater than 99.9%, and only several ppm of the laser beam is observed by the mirror. Thus, it is not burned. The innovation is in generating a laser beam between two such highly reflectance mirrors, one on the cubesat, another shown on the right side. Note that a thin disk laser gain medium that generates laser beam is located between the two mirrors. Here, the laser beam is recycled about 1,000 times to amplify the laser power and the photon pressure on the mirror. Thus, the actual power to generate 450 kilowatts laser beam used only about 1 kilowatt of total electric power. Without the recycling, we will need a 450 kilowatts laser system, which has the size of a small building. I repeat here one more time because of its importance. Success was rewarded with the 2017 Nobel Prize, Physics Prize. Here, the two mirrors are separated by 4 kilometers. So, what is the difference between this optical cavity and the depth of a photonic laser thruster? Here, I remind you that the two-mirror system is called an optical cavity. The upper picture shows the anatomy of the gravitational wave detection system. Here, the laser beam is generated outside of the cavity and injected into the cavity. By multiplying the photon impact pressure, they could decrease the shock noise of individual photon impact on the mirror of a probe and achieved the sensitivity of detecting a mirror distance change in the amount of size of the nucleus. Truly amazing achievement. This sensitivity permitted to detect mirror probe movement by gravitational waves. However, such a system cannot be used for propulsion because even a slight movement of a mirror will rapidly decrease photon pressure. In December 2006, under the auspice of NASA, it was accidentally discovered that such a movement sensitivity of the mirrors in the cavity can be eliminated by inserting the laser generator inside the cavity, as shown in the lower diagram. It was a simple idea, and anybody could discover if if the circumstance was right. When it was discovered, I could not believe it and initially thought it was an experimental error. The experiment was very difficult because of, at that time, large thermal noise of a weight scale used for measuring photonic thrust, and because of the excess laser power observed by dust particles in air. And because, of course, it's done under low budget, small experiments. After months of repeating the experiment hundreds of times, I was convinced that the discovery was real, and this led to the birth of a photonic laser thruster. The central idea in the photonic laser thruster's optical cavity is that left mirror and laser generator located within the cavity of the mirror powering system, or laser powering system, can be physically separated from the other mirror-mounted unpropelled spacecraft. And the details can be found, the publications listed in the under the chart. Under the auspice of NIAC and NASA, we were able to scale up the laser power and the thrust by a factor of 100, and the dust problem was eliminated by performing the test in class 1000 clean room environment. A defining moment was when the CubeSat was propelled by the photonic laser thruster, as shown in slide 10 and the demonstration video. Before that, me and my colleagues bet on it, and we bet about 50% chance of moving the mirror. But we beat the chance. The experiments now became much more definitive, and we firmly established a new type of a thruster stand system to accurately measure the photon pressure delivered on the mirror, as shown here. Because of the time constraint, the details are suggested to be read in our recent paper listed below. So, thrust efficiency, that is the ratio of the generated thrust to input energy as a function of the specific impulse ISP. Please note that the plot is in log-log scale. As ISP increases, the thrust efficiency decreases approximately linearly. Thus, the low ISP thrusters, such as chemical thrusters, are more efficient than the high ISP thrusters, such as electrical thrusters. Because of the special theory of relativity, the maximum ISP that can be achieved is 3 times 10 to the 7 meter per second, which can be achieved by photonic thrusters, as marked by a red field in circle right lower part of the chart. The photonic thruster, as in solar cell, has the lowest efficiency among all thrusters, as you can see. However, in photonic laser thruster, the photons can be recycled between the source and the spacecraft, resulting in enhancement of efficiency. We have demonstrated the recycling factor of 1000, as shown in the right upper golden circle, with the projected recycling factors of 10,000 within the reach of the state-of-the-art of high-power laser technologies. Thus, it is feasible to build photonic laser thrusters that can be better than the traditional electric thrusters in efficiency. This finding is truly profound in rocketry. A model of NASA's 10 megawatt nuclear spacecraft for Mars using NEP, nuclear electric propulsion, is illustrated here. It has 2 5 megawatts reactors and large liquid hydrogen tanks for propulsion system. One important aspect here is that spacecraft system has to carry a large nuclear reactor system, propellant and propulsion system in its journey wherever it goes. Acceleration and deceleration of such large, heavy systems uses most of its energy, and only little energy is used for moving crews and cargos. And there is similar design of the spacecraft powered by solar power. But I believe that beyond the 10 kilo, somewhere around 100 kilowatts or somewhere around megawatts, nuclear power will be much more practical. That's the reason I am showing this diagram here. This picture conceptually illustrates a preliminary sketch of a PRT, Photonic Laser Thruster system built on a 10 megawatt nuclear spacecraft platform. The nuclear powering system with minimal propellant system for attitude control and station keeping can stay on Earth orbit, while only the crew and cargo vehicle with mirror and thermal management and attitude control systems is accelerated by the recycled laser beam to Mars. On the opposite end of the Mars, of course, another similar spacecraft powering system will decelerate the vehicle into the Mars orbits. Thus, Photonic Laser Thruster system enables the separation of the crew and cargo vehicle from the powering and propulsion system, resulting in unprecedented capabilities beyond the reach of the conventional rocketry. A very interesting aspect of such systems is that nuclear spacecraft can be configured for both for electric propulsion and the photonic laser thruster powering system, and can by itself go to Mars with electric propulsion and be ready for receiving vehicles from Earth or Moon. Thus, two of such systems will constitute a round-trip photonic laser thruster system, a Photonic Railway, which is within the reach of existing rocket technology. 18. When scalable in the future, the Photonic Laser Railway can be envisioned. Here, the space train is accelerated and decelerated at 1g by photon pressure to the halfway point of the travel, such that the crews will experience an Earth-like gravity environment. When such transportation system could be built, it would take only 3 days to transit to Mars. In the multiplanetary civilization, both the conventional thrusters, such as chemical and electric thrusters, and the photonic laser thrusters are predicted to be used together in conjunction, however, for different purposes. For example, conventional thrusters will be used for initial transportation for establishing the base structures, transportation of low-priced commodities, and the transportation of very large or heavy commodities and equipment. In particular, nuclear spacecraft configured for both electric propulsion and the photonic laser thrusters powering system can by itself go to the destination with its electric propulsion and be ready for receiving vehicles coming from the opposite side. On the other hand, photonic laser thrusters, Photonic Railway, can be used for rapid transit of humans and animals, rapid transportation of high-priced commodities equipment, smaller or lighter commodities equipment, automatic. Also, it can be used for automatic wireless powering beam through the laser beam to the cruise and cargo vehicle. Truly, the possibilities are limitless. Eventually, it is predicted to be feasible to construct large-scale Photonic Railway that will connect the Earth to the edge of the solar system and possibly the Kuiper Belt. A cartoon that represents such endeavor is shown here. I'm hoping that such a system will eventually be able to send humans to exoplanets in the far future, probably not within our lifetime. This table shows examples of required PRTs for various transits in the solar system. Here we assume the transit vehicle has a mass of 1 ton, and we assume 50% of cargo and crew capabilities. The transit from Earth, GO, probably that's one of the favorable orbits, to Moon may require smaller delta V. For example, here it is set 11.6 kilometers per second, which will take about, and the trip will take about 20 hours. Such a system will require a 10 megawatts electrical power that can be powered with existing nuclear rocket platforms and a laser powering distance of about 100,000 kilometers. The required mirror diameter of the power system and that of the transit vehicle are 30 meters and 4 meters respectively. They can be built on lightweight, thin structures. For achieving delta V greater than 100 kilometers will require further technological development beyond the state-of-the-art high-power laser technologies. However, it is projected to be feasible. For transits from Earth to Mars, delta V of 141 kilometers per second will make the transit in 18.5 days. And the laser powering distance in this case is 300,000 kilometers. This will require the mirror diameter at the power system and the transit vehicle are about 50 meters and 7.5 meters respectively. And I believe this can be done through by maximizing the existing technologies. A similar PRT system will take a transit vehicle from Mars to asteroid in the asteroid belts in 5.6 to 18 days. Transit to selective asteroid may take a longer time, however. With such a transit time and reduction in propulsion energy requirement, the asteroid mining will become much more attractive and profitable and realistic. Eventually, with a 1 gigawatt photonic laser thruster, the transit from Mars to Jupiter and its moons may take only 45 days. It is predicted that once humans are able to use the resources from the asteroid belts, a true multiplanetary civilization will begin.
Excuse me, Young?
Yes.
Yes, I'm trying to understand, what is the laser powering distance? I don't understand.
Laser powering distance, yeah, that's a very good question. Because we can indefinitely power the laser over a long distance you can imagine. However, because of the diffraction limit, beam diverges. Therefore, the size of mirror increases accordingly. So within the practical limit, we set the diameter of the mirror that can be achievable, and then that will determine the laser powering distance. So once the laser beam goes over that, then it becomes less because it will spill over the mirrors. So that's a laser powering distance.
Well, I guess now, but the laser power distance, that's the distance between the laser and the mirror. Is that correct?
Yes.
Oh, okay.
That's a maximum distance.
Okay. Well, I guess I understand the first row, because where you're saying if you have a laser in geo and you're sending
Yeah.
something to the moon, you want your
Yeah.
laser power distance to be something on the order of the distance to the moon, which is a couple times 10 to the 5 kilometers. But
Yeah.
if you're going to Mars and you have a laser on the Earth, 3 times 10 to the 5 kilometers is about 1/100th of the distance to Mars. So that
Yeah.
doesn't work as well.
The reason is that the technology for making the mirror is limited. So, and also the weight of mirror structure will increase dramatically as we make a bigger and bigger mirror. So we are limiting. In fact, the laser power distance is limited by the mirror size. They can be manufactured with the existing technology or projection of the existing technology. That's the reason. Otherwise, in the far future, if the mirror technology evolves and if we can build bigger mirror, then of course we can go all the way to the destination in terms of laser power and distance.
Oh, okay. I guess what I'm saying is if you have a laser on the Earth and you're trying to push something to Mars, you need a laser power distance about 3 times 10 to the 7 kilometers. 3 times 10 to the 5 kilometers isn't going to do it.
Then the mirror size becomes too big.
It's a burn and a coast. You're ignoring the coast. It's a burn and a coast.
Yeah, okay. I see. That's interesting.
Yeah. So this is the chart is designed so that we can achieve in the near future with the existing technologies or with the projected technologies.
Okay.
And then that's the reason I said, for example, the slide 18, that's far future because it will require large mirrors, which is beyond the reach of current technology. Plus, another thing is, of course, if we can develop scientific technologies for controlling the diffraction limit, I believe that will happen. Then, of course, the laser powering distance will decrease.
Okay, that makes sense.
So this is sort of the near-term or mid-term roadmap.
Okay,
I think it's doable.
Okay,
and you're welcome. That was very good question. Very, very good question. Thank you for pointing that one out. And so, okay, we talked about overall general plan. Please.
I'm sorry, I had a question on this too.
Yes.
This assumes this chart on 21. You do have another laser power source at, say, Mars, doing the deceleration, or is this a flyby?
Yes, you can put another one in the destination site, and that's the reason I said
you have the 18.5 days. Does that include the deceleration, or is this just a flyby? This is a one-way flyby. One-way flyby. Yeah. Okay.
Yeah, one-way fly. It's a one-way travel time. One-way flyby.
So it'd be about.
Deceleration would be about twice more. Yeah.
Yeah. Okay, got it.
If you want to, yeah. No, I would take back. Deceleration would take a little less because little more than 18.5 days because we only decelerate 3 times 10 to the 5 kilometer, 1/100th of Mars to Earth distance. But then
the deceleration time equals the acceleration time. It's in the third from the right column.
Yeah. So acceleration time is 1.2 hours, and deceleration time will be 1.2 hours. So it's basically whether you decelerate or not, it takes the same. Yeah.
I get it.
As you can see in this chart, by the way, 21, laser powering time is small. And then G-force is also concerned because 3.4, you cannot go too long, 3.4 G. So all these things are concerned together. But of course, all the parameters will be tweaked once we want to really launch the vehicles. Okay. Slide.
Say, hold on, Young. This is Harley. I've got my turn for questions. By the way,
Please go ahead.
Thank you. This is very helpful. This is a great chart. And you note at the top that this was for a 1-ton payload.
1-ton vehicle. And 50%, I project 50% would be passenger cargo weight, and we may have to carry smaller conventional thrusters for altitude control, that kind of thing, because the trajectory is really far, you know.
And I was just noting here that the models that I've seen, the architectures I've seen for a payload for, quote unquote, typical human missions to Mars, probably in the neighborhood of plus or minus a few 100 tons. So that, which of course would decrease the travel time because of the mass that you have to accelerate. Or am I missing something?
Harley, or is that a propellant?
Excuse me? I'm sorry. I spoke over you. I'm sorry.
Is that an inert mass, or is that a propellant? I don't think they're 100 inert mass, are they?
Well, I think they can. Yeah, I was thinking that you'd have, of course, a few, maybe several tens of tons for the hab. Then, if you want to take with you, although you probably could pre in place if you want to take your supplies, your logistics systems, and so on. So when I said a few times 100 tons, I was probably exaggerating by a few. So let's say 50 to 100 tons.
Yeah. Well, Harley, what you have to keep in mind also is that the transit time is vastly less than the transit times you're thinking of.
No, I know that. I was absolutely right. So you'd be traveling, say, in a Volkswagen rather than a Caterpillar truck, and you're exactly right. However, you're going to be taking, if you're going to go this route, you still will need, presumably, will need supplies on the surface and et cetera, that sort of thing. You might want to take a lot of people.
Harley, that's a very good question. In fact, slide 19, if you go back, you see the scenario there. Conventional thrusters will be used for transporting large and heavy commodities. It's almost like a oil container or oil tanker, something like the kind of structure, slow but carrying large stuff. But then you need to have a jet airplane. There will be the Photonic Laser Thrusters. Okay. And another thing is that this is based on 1-ton vehicle because it's a scalable. Okay.
Right.
Depending on how of course. And then also if we can increase the laser power distance, and then mirror size goes, but then also we can increase to 10 tons or 100 tons, depending on. So it all depends on what will be the development. But this is the initial roadmap that we can demonstrate with probably breaking the national budget. Okay.
Okay.
So these are doable. Surprisingly, that's my surprise too, that I found in the last 4 or 5 years. The slide 22. So what is the next step? How can you, because this is new rocketry, so we need desperately a space demonstration. We propose a 1 Newton Photonic Laser Thruster demonstration on ISS, which has 100 kilowatts solar power system and other cooling system that can be readily tapped in. A conceptual design for the demonstration is illustrated here. And the pump laser power for energizing the Photonic Laser Thruster is about 20 kilowatts, and the total electrical power required is 40 kilowatts, well within the ISS power capability. So you can probably run your computer while we are shooting the Photonic Laser Thruster there. This will be truly remarkable because we can do 1 Newton electric thruster. 2U cubesat with a 2 kilogram, for example, will be accelerated to delta V of about 100 meters per second, which will require a maximum laser powering distance, 10 kilometers, and for duration of 200 seconds. Like what I said, the distance is limited by, in this case, the aiming technology because the budget will be lower. So laser aiming, tracking plus the powering distance on all those, and consider that I think 10 kilometers is highly doable. The demonstration is proposed to be performed in the Japanese experimental module or in other module, but some other people suggested it. Equipped with the robotic arms so that we can maneuver around cubesat necessary, if it's necessary, with the system, formation flying over the cubesat and ISS together with the distance up to 1 kilometer can be also demonstrated according to the preliminary calculation. The demonstration is projected to be accomplished in 3 years if we start work on it, because the system can be mostly built with off-the-shelf items, surprisingly. So we can shoot the 1 Newton photonic laser thruster with mostly off-the-shelf items. That shows the advancement of the high-power laser technologies. And of course, these are in public domain hardwares. The next step beyond the ISS PLT demo is, I believe, a lunar suborbiter launch demo with a 50 Newton PLT, photonic laser thruster. Here, photonic laser thruster will be powered with a 1 megawatt solar or possibly nuclear power plant, which will be much more compact. Demonstration over launching a 20 kilogram spacecraft to achieve delta V over 1 kilometer per second, approximately. It can be higher or lower depending on what we like to achieve is proposed. The required laser powering distance here is about 200 kilometers. We discussed about that thanks to Dan Lester with the duration of 400 seconds. So we can shoot as many as possible if we want a day, maybe 10 times a day, even more. The proposed demonstration can be achieved in 10 years in parallel with the lunar agenda of NASA and other international agencies and companies. Eventually, the demonstration will be rapidly developed into various cislunar transit modalities, including the shuttle between lunar sites for rapid transporting crews and cargos, as illustrated in this drawing. And the details here, we do not have time, so I'm not going to go to the details, but basically a lot of things can be done on Moon with the photonic laser thrusters without using slow rovers or without using precious propellant. In conclusion, photonic laser thruster has been successfully demonstrated in lab, and its theory is now established for its performance projection. The photonic laser powering system is projected to be more efficient than that of electric thrusters with a similar thrust. Photonic laser thruster system does not need to carry propellant or power supply and the engine. PRT is projected to open. Somebody is playing music. Thank you. That means my time is almost out. PRT is subjected to open multiplanetary, projected to open the multiplanetary civilization. Moon is projected to be a gateway to Mars with the PLT. Mars is proposed to be a gateway to mining asteroids in the Asteroid Belt and a major manufacturing refining hub. The ISS PLT demonstration in 3 years is proposed to be the next step. The lunar suborbiter launch in 10 years is proposed to be in the second next step. The PLT transit to Moon and the shuttles are projected to operate in 20 years, I believe. The PLT transit to Mars asteroids are projected to operate in 30 to 40 years time frame because we may need a nuclear space rocket. The resulting endeavors are the true indicator of the multiplanetary civilization. Slide number 26, please. Lastly, I would like to acknowledge the support of the NIAC and NASA and the work of colleagues and collaborators. Thank you very much for your attention.